Hello everyone. In this video we're going to begin our discussion of how we can use asymptotic notation to understand the runtime of functions. So here we have a function, func1, the ever creative name, and we're going to analyze how long does it take. We're going to begin by saying let t of n be the running time. We'll pretty much always use this notation, so it's not going to matter too much, but for now we'll use it. What we're going to do is say that whatever appears inside of those loops, those are the dominant thing, is going to take some constant amount of time c. We then need to find out how many times does line 5 execute. If you remember from Foundations 1, we can express the runtime of for loops using summations. So t of n is equal to the sum from using the same bounds as the for loops, I equals 1 to n, times the sum from j equals 1 to I of the cost of whatever appears inside of that for loop, which is just c here. This equals, the inner summation there can be simplified to c times I. That's c times the top bound minus the bottom bound plus 1, because we're including both bounds. Now, we need to figure out how to analyze that summation. Let's write out what the terms are. We have c times I equals 1 plus I equals 2 plus I equals 3 plus up until n minus 1 and n. Now we dig deep into the memory banks and maybe we remember what that equals, or we can do a quick derivation, because this derivation might actually help you remember what the formula is. So I'm going to off to the side here to do a little recall. We have 1 plus 2 plus 3 plus up till n minus 1 plus n. I'm going to rewrite that summation again, but in the exact opposite order. So I'm going to have n plus n minus 1 plus n minus 2 plus all the way down till we get to 2 till we get to 1. If I was to add up those two summations, the first term would be n plus 1. n minus 1 plus 2, that's n plus 1. n minus 2 plus 3, that's n plus 1. Plus n plus 1, plus n plus 1. Every single term is n plus 1. And to maybe make this more rigorous, I'm going to call the first summation x. The second summation is also x, which means the green summation is 2 times x. How many things are appearing on the right-hand side there? Well, there's n terms in the first one, n terms in the second one. There's also n terms in the third one. So it's n times n plus 1, which means that original summation would equal n times n plus 1, but I got to divide by 2. So we have that exact summation appearing over here on the right. So this equals c times n plus 1 all over 2. Then we try and identify what is the most dominant term there. It's going to be n squared. So this is in theta of n squared. Let's now look at a slight modification of that same function. What if I had an if statement at the start that says if n is very large, in this case greater than 100,000, then we return 0. Otherwise, do the same thing we did before. This is a bit tricky, but all we care about is what happens when n is arbitrarily large. In this case, for large enough values of n, all we are doing is executing the if statement part. So the runtime of this function is definitely bounded by whatever the largest value of n I could obtain and do that for loop, which would be n equals 99999. And we could plug that into the same analysis we did before to get an actual number if we wanted. So this horrible mess of a function here, by adding in the if statement, which goes from being in theta of n squared to being in theta of 1. It's bounded by a constant, even when it might take a while for that particular value of n. How about a third example here? What if we change that inequality in our if statement check? Here, if n is small, less than 100,000, then we return 0, and if it's large, we got to do some work with the for loops. In this case, for large values of n, we're always executing those for loops, so the runtime here would be theta of n squared.